All right, folks, here is a lesson on the FRQ from week 14 Friday. Okay, so let's take a look at the FRQ part A. Okay, part A, remember graphing calculator was okay on this one. In fact, you needed it for this one. Okay, now, so let's look at 5A right here. Okay, now, you got this function over here, okay, which is f prime, okay? It's not regular f, it's f prime. And Desmos, okay, looks, if I were to plug in the blue function and look in between x values of 1 and 4, I get that right there, okay? Now, just to give you an idea, a little cheat, so to speak, of what it's supposed to look like. Now let's go back to our graphing calculator here. I literally plugged it in, okay, right here. All right, plugged in that blue. And then I set the window, I put 1 and 4 for x values, and that's from this right here, okay. And then I click graph, and I got this. Now how do you produce these points over here? Okay, what I like to do here is zoom in, okay? I'm gonna zoom in real quick. Let's play with the window first. Let's go -5, 5. Let's change that to -5, change this to 5, okay, and graph, and let's see what happens there, okay? Okay, that is better now. Okay, now let's say we want to find these two points right here. Those are our x-intercepts. Okay, the way you would find those is you go second, and I taught you this before, I believe. You go second 0, 0 is synonymous with x-intercepts. You would put, let's find that 2, 0 on the left side first. Our left bound is our left wall, because right now our calculator doesn't know where to look for your x-intercept. So that's my left wall, and here is my right wall. Okay, so it's going to look in between these two, and at guess question mark, press enter. Okay, and you will get roughly 2, 0. Okay, so it's in the end it's an estimation. Okay, it's not going to be perfect, but you can just assume that's 2. Okay, I just want to make sure I typed in everything correct over here. X squared minus 4x plus 4. Yes, I did. Okay, and you do the same to find the other blues. Now, how do you find these blues right here? Okay, how do you find these blues right here? Okay, well, I am going to go back to graph, second calc, and I'm going to, for this bottom blue, I'm going to go minimum. And I am going to put the left bound somewhere there. Doesn't need to be exact. Okay. And put right bound here. And let's see. The minimum is 2.473, and this matches up with the bottom blue. Do this for this point right here. Do the same thing except do maximum. Okay. Do maximum. Okay. Now, I want to pull something up over here from Google Classroom, okay, Google Drive, sorry. It is here. Let's actually go to Google here. Okay, this is from Unit 5, and there were some, there was a slide in particular right here, 5.1 to 5.3 concepts. Okay, and let me scroll down here. Let's download this so it doesn't need to load. Go to downloads. Let's load it up here. And let's scroll down to here, right here. Okay, I want to get that ready to go. Let me zoom out right here. Okay, boom, copy, paste right there, and let's get that ready to go and save it. Now, okay, so now you know how to get all of these points right here, okay? And now we got to just analyze it, but let's just, because it's a cleaner, it looks cleaner on Desmo, on Desmos, and let's, for the sake of keeping it flowing, let's just use this right here, okay? Now, our critical points are going to be here. Critical x values are going to be here, here, and here. Remember, our critical values is where your x values are, or your first derivative is equal to 0 or undefined, okay? There are no undefineds, okay, in between 1 and 4. You can see it's continuous, so we're just working with these 3 points, okay? Now, let's go over here. We know, okay, we know that this is a maximum when the slope changes sign, okay? So we can actually just do this. We can do the number line, okay? We'll use the number line here, like we did before. And we'll go 2, we'll put 0 here. We'll just shift 0 over to the left a little bit. We'll go 2, 714, and 3.772, and we'll stack it like this. Now, here it is to the left of 2, your derivative is going to be negative. Look, this is negative. To the right of, in between 2 and 2.714, it is still negative. That's this portion here. Okay, this u right here, I should say, right here, that's still in the negative zone for the first derivative. Okay, and here between 2.714 and 3.772, it's positive. Okay, as shown here, this is positive. That's on the that has positive y values. Now after 3.772, it is negative. Okay. And so remember, this is your number line for your first derivative right here, okay, f prime. So when you're, remember, f prime is your graph of slopes, okay? So when your slopes change from negative to positive, you have a minimum. And when your slopes change from positive to negative, you have a maximum. And that is why here you have a minimum at 2.714, and here you have a maximum, okay, at 3.772. And that's part A. Part B and C, pretty easy stuff. That is your linearization, okay? So again, what you want to do, okay, so if you look at, so basically, we want to find, we don't know, in this case, we don't know the graph of f. We can't see it. Okay, we only have the graph of f. We only have the graph of f prime. Okay, but the process is still the same. Okay, let me see if I can pull up a key. I think I can do this under scans, and I had a key. No, it wasn't that one. Oh, I know where it's at. Okay, I'm going to go to unit 5. And here we go, 5.5, 5.6. And let's pull up the key here. Yes, right here. Let's pull that up. Now, so the goal here was the big picture with linearization. we have this function, okay, and the first thing to do is to find the derivative of this, okay. So we have this function. The big picture of linearization is this. So in this case, I'm going to make up how this function looks, okay. So in this case, we got maybe something like this, okay. And I'm going to make up an x and y axis, and we have x equals to 3. So let's say x equals to 3 here, okay. 3 comma something, and let's say we create a line based on the derivative, okay. And so what you do is you take the derivative of this gray right here, which becomes this. You plug in 3 into the derivative and you get negative 23, which is the slope. So the slope right here is negative 23, okay. And remember, our point slope form is y minus y sub 1 equals to m times x minus x sub 1. So this negative 23 that we got through plugging in 3 into the derivative, okay, that's going to be negative 23 right here, okay. And we have the x-coordinate, which is 3 right here. We just need the y sub 1. So you literally plug in this 3 into, okay, you plug in the 3 into this, okay, right here, and the 4x right here, and you will get negative 20, okay, and that gets plugged in here, and you basically have point slope form of the equation of this line right here. And we use this line right here to predict what 3.4 would be. So we would plug in 3.4, okay, 3.4 into x, okay, and it would spit out a y value, which in this case is negative 29.2, okay. So when you basically plug in 3.4 here and get y by itself, okay, I should put blue here and say minus 20, okay, and that's from here. Okay, so when you plug in 3.4 and isolate y, you're going to get negative 29.2, and obviously this picture, this graph is not drawn to scale because this looks like a positive value. It should be somewhere down here. So this line, based on this line, okay, you have on this line, I should say, 3.4 gives you a y, 3.4 for the x value gives you a y value of negative 29.2. That's what this line predicts, okay, so that serves, this negative 29.2 would serve as a prediction of what it might be on this graph right here, okay? But we find out that the graph, if we plug in 3.4 directly into the function here, we get negative 30.704, which is kind of close to this. And again, this is this line is going to be an overestimation because the graph is concave down, as you can see. Now, I just gave you a review of linearization so that we can now approach this a little faster. Okay, now that we have context over here. So now we basically want point slope form y minus, okay, y sub 1 equals to m minus x and x sub 1. Okay. Now we don't know this original function, so we can't take the derivative. But check this out. This is the graph already of the derivative. Remember, this graph right here is of the derivative, as you can see right over here. That's the derivative. Okay, that's what's given in the problem. Okay, so this is already the derivative, and so at 1.5, we don't need to manually calculate the derivative. We know the derivative, the slope. We don't need to manually calculate the derivative or slope because it's given to you as negative 2.1. So right over here, okay, I'm going to rewrite this and say negative 2.1 103. Okay? All right? And on your calculator, what you can do is literally go back over here and go to graph and type in press trace and go 1.5 and press enter, and it spits out. Okay? It spits out the y value. If you want to find another y value, 1.6 for example, press 1.6 and then press enter. So our calculator gives us this. Now we have to find x sub 1 and y sub 1. Well, x sub 1 is given to us. That's 1.5. Okay? And let's see, how do we find f of 1.5 when we plug it in? Give me 1 second. Oh, it gives it to us right here. Okay, so that's given to us at the very beginning. F of 1.5 is 3. Okay, so whereas you would normally plug in, for example, in this previous example from the test, you plug in 3 to get the negative 20. Okay, we don't need to plug in this 1.5 because it's given to us in the beginning over here. It says it's plugging in 1.5 into F will give you 3. So we get 3 over here, which is given to us earlier. And then we get the 1.5 over here. Okay, so boom, and it's given to us. Now here, now we literally, all we need to do for 1.8, we just plug in the 1.8 here and solve backwards to isolate for y. Okay, now for C, remember here, okay, for part C, remember here, this graph was concave down, so the linearization was a overestimation. Okay, now if you look over here, we actually don't need this. All we need to know is here, this is concave up because it's positive, so then it's going to be an underestimation. That's all it is. So our linearization, our prediction over here, when you isolate y, whatever you got for y is going to be an underestimation because this was concave up. Okay, remember, if it's concave down, which is here, then it's an overestimation, and vice versa. If it's concave up, is an underestimation. So concave up, underestimation, that's part C. Okay, all right. Now, here, and again, it's concave up is given to us right here. Now here, D is really easy. Okay, why the average rate of change cannot equal to 6.5. Okay. Now, remember the average rate of change over here. Let me get this. Let's copy and paste this here. Okay, boom. All right. Again, I'm getting the Desmos one because it's a little bit cleaner. Okay. Okay. Now, remember, mean value theorem is basically, let's say you have a function here and we have a point here and a point there. Now I'm going to make something up. Let's say that this right here is, okay, 3, 4. Okay. Let's say over here, this is, I don't know, 7, 4, 7, 15. Okay, and if you do the y, if you subtract these two, if you do the y sub 2 minus y sub 1 over x sub 2 minus x sub 1, you'll get 15 minus 4 over 7 minus 3, which becomes 11 over 4. That is your slope that is in between these 2 points, these 2 endpoints here. So all the mean value theorem says is that there has to be some other x values if the function is continuous. Okay, if the function is continuous, here, let's pull it up right here. Boom. This is what it was here. Okay, whoops, let me put it like this. Here you go. For the mean value theorem, if it's continuous and differentiable, okay, which it is continuous because you can draw it without lifting your pencil, is differentiable because there are no corner or cusp, okay, or any discontinuous parts. Discontinuous parts or corner or cusp makes it undifferentiable. So it meets those two requirements. All it's saying is that there are going to be at least one x value where the derivative at that x value is going to equal to the derivative of the endpoints. Okay, in this case, in this hypothetical case, it looks like there's 2 points. Okay, so basically, why can't the average rate of change of the interval cannot equal to 6.5? Okay. So remember, this is the graph of the derivatives. It's not the graph of, it's the graph of f prime, which is the derivative. It's not the graph of f, okay? Now, the simplest way to answer this, okay, well, let me say this. You don't know the endpoints. You don't know, you can't do this whole process here because you don't have the graph of f, and therefore you don't have the graph, the endpoints between 1 and 4. Okay, the x and y values. You have the x values, okay, it's 1 and 4, but you don't have the y values because you don't know the function. You don't know what the function is. Is it x squared plus 4? Is it x cubed minus? We don't know, okay, it doesn't tell us that. Nor does it give us the graph. But we have enough information to infer what the answer to this is going to be. Now, the most direct and simple answer is this. The average rate of change will never and cannot equal to 6.5, okay? Because, look, the graph of slopes, there's no such y value that has a that is 6.5, okay? So let's say the slope here between the endpoints is 6.5, okay? There is going to be no c value, which is the x value really, in between 1 and 4 that has a slope of 6.5 because look, what x value, okay, what x value anywhere here has a y value of 6.5? Here the y value is negative 0 point whatever. None of these and anything in between, this function never reaches to the top here of 6.5, okay? So because this function, because this right here never reaches a y value, the ceiling of 6.5, therefore the average rate of change, okay, cannot equal to 6.5, okay? All right. Okay, that's the most direct way of answering that, okay? So therefore, it's kind of going backwards now because this graph never reaches a ceiling of 6.5. Therefore, the endpoints, the slopes cannot equal to 6.5. Okay, all right. Because remember, the average rate of change is just y sub 2 minus y sub 1. Okay. So before we kind of said, okay, if the slope is equal to 6.5, then at some point it needs to be 6.5 in between. Okay, now we're kind of just reversing that. We're saying because there is no 6.5 slope in between 1 and 4, therefore the endpoints cannot have a slope of 6.5. Okay, and again, the function is continuous and differentiable. Okay. Okay, and that wraps up this recap of the FRQs. Thank you for tuning in, folks.